So we're going to have a one input counter, if you like, that just goes on and off. So we'll use output A, which is the units of a binary count, and it'll have two values of either off or on. So that's the truth table input for A, the binary count. And then we can decide which characters to have on the output as the binary count changes between 0 and 1. We could have two different characters, or we could have the same character twice, which would be a little bit pointless. But I'm going to do H and I for hi, to say hello, say hi. So when A is low, we'll have the H showing, and then when A goes high, we'll have the I showing. And if we just remind ourselves of what the 7-segment display characters are, we've got A at the top, then it goes clockwise around the edge, B, C, D, E, F and G in the middle. So let's put our segments as outputs in the truth table, F and G. And for character H, for that to be illuminated, all of the segments are lit apart from A and D segments. So we can make segments A and D low for the first part of the count, and all the others are high or illuminated. Then when the input goes high, we're going to have the letter I. So the only two segments that are illuminated for the type of I that I've shown are B and C on the right. So we can put a 1 for outputs B and C segments, and everything else is 0. So let's look at the Boolean expression for segment A. Well, this is pretty easy because A is always off. So A equals 0, and that equates to being connected to ground or 0 volts. B, the output segment B is always on. It's always logic 1, so we connect that to 5 volts. As you notice, segment C is the same as segment B. C is always on, D is always off, and A and D are the same. So A equals D and B equals C because they are the same all the time. And then segments E, F and G, they're all the same. So E equals F, which equals G. And the Boolean expression for them in terms of the input is that they are high when the input is low, and they are low when the input is high. So all three of those are worth not A, the complement of the A input value. Now, because this is such a simple circuit, we could just have an on-off logic state for the value of A, but I've got a 4-bit ripple counter, which I've put some buffers on the outputs to make sure that there's enough juice or current to drive. And I've also put wire labels for the output A, and I've put NA for not A, and I've done B and not B, C and not C, and D and not D as well. So then we can just wire to those directly later if we want. So I've added the 7-segment display. We need a ground for the display, but we also need a ground for some of our Boolean logic because some of the segments were equal to 0. And in generator mode, we need a DC supply, which I will rotate. And we're going to make that a 5-volt supply to supply the logic 1 for the 7-segment Boolean expressions that were equal to 1. So I've made that 5 volts. And then we'll just wire up the 7-segment display according to our Boolean expressions. So segment A at the top was always low. D equals 0 as well. And B and C were always equal to 1, so we'll wire them to 5 volts. E, F and G were equal to not A, so that's the complement of variable A. And then I'll wire F and G together with E. I need a ground for the 7-segment display, then I'll simulate. And it's doing what we wanted it to. And it's just a demonstrator for more intricate circuits with longer messages, which we'll get onto. What I want to do is add a second 7-segment display, and I want to delay all of the 7 segments by 1 clock cycle, hence all of these flip-flops, so that I can have 2 7-segment displays that scroll. So input to the first flip-flop will be segment A, the input to the second will be B, and so on. B and C are the same, so I could have saved myself a few flip-flops if I wanted to on this occasion, but I'm just wiring it up fully. D is equal to segment A, and the delayed segments E, F and G, they're all the same as well. So I didn't need to give them individual flip-flops if they all have the same value, but I've done it fully just for this one. E, F and G were equal to not A, so I've wired it up to the complement of A from my counter. Get a second 7-segment display. Then each output will go respectively from A to G, and these will be delayed by 1 clock cycle, which will show the message scrolling when I move the 7-segment displays around. Need to ground the second 7-segment display. I'm going to call this the right hand display and then the left hand display using text labels. I need to clock all of the flip-flops with the same clock signal, the master clock for my counter. Then I'm going to right click it and add a wire label, and I'm going to call it clock, which is the same as my master clock was labeled. Then simulate. First the right hand side display says H, then it says I, then it moves on to the left hand display with a delay of 1 clock cycle through the flip-flops. And this is just a demonstrator to show the workings for more intricate circuits, which we'll get onto shortly. I'll move the left one to the left and the right one to the right. I'll move the clock down, zoom in a bit, and simulate. So that's pretty cool, and we're building upon stuff here to get more complex scrolling messages. So now I want to make a 5-character message, so I need 3 bits of binary count to count between 0 and 7 to say hello, like Stampy does. We're going to do H, E, L, L and O, and we're going to figure out the truth table for each of those letters. So when the counter is at 0, 0, 0, like the 0 count, I want all of my displays to be completely off. So I will put the segments at logic 0. For the H, only A and D are low. All the others are high. For the E, segments B and C are low. All the others are high. Then for the L and the O, if we just remind ourselves of the segments, for L we need D, E and F to be illuminated. And there's 2 L's, so we'll do it twice. All the others are not illuminated. And for the O, they're all turned on apart from segment G. And then for the last 2 counts, which I could put anything in, I'm going to make them 0, so they're fully off. So we need to find Boolean expressions for each segment, and segment A is only on twice. It only has two states when it is at logic 1, and they are not C and B and not A, or C not B, A. I'll cross them off as I go along so I don't forget any states. And that can't be simplified because there's too many changes between the two terms. For segment B, it is also illuminated just twice through the full count. That's not C, not B and A, or cross it off, C, not B, A. But if you notice, these two terms have redundancy. They both have not B and A, but then the C or not C is irrelevant through the complement law, because the value of C obviously has no effect if both of those terms are true. So segment B is equal to not B and A. Segment C is always the same as segment B, so we can just wire up B and C together because C equals B. For segment D, I'm going to use negative logic. I'm going to look at when it's low because there's some nice pairs that we could use the complement law. So I'm going to say not D is equal to these four cases. So that's not C, not B, not A, or not C, not B, A. So there the A is irrelevant. Or CB not A, cross it off, or CB A. And again, the value of A is irrelevant there through the complement law, because we have common factors of not C, not B, and that's A or not A, and CB, A or not A, and anything odd with its own complement is 1. So it proves that the A has no effect. So the Boolean expression for not D is not CB or CB. So we'll use a NOR gate instead of an OR gate to get the positive output for segment D. I'm going to do the same for E. I'm going to see when E is low because there's only 3 states, so it'll be quicker. And there's a nice grouping at the bottom, which we can use the complement law like for segment D. So we have common factors of C and B, A or not A, so A makes no difference. So it's going to be not C, not B, not A, or CB. But we can't simplify further because there's too many changes. Segment E and segment F are identical, so we could say not E equals not F, or we could say E equals F. So we can wire E and F together, save a bit of time and save some logic. Segment G, I'm going to use positive logic because there's only 2 states when it's high. So we've got not C, not B, A, cross that one off, or the other time when it's on, not C, B, not A. There's too many changes, so that is the minimal expression for segment G. So let's have a go at wiring it up to make our 7-segment display say hello. So we'll go back to Proteus and place a 7-segment display. We'll need a ground for it. I've no idea why I put it all the way up in the top right, but I'll move it. And we've got our components mode. We need to build up the logic, so we need AND gates, OR gates and NOR gates. So for segment A, we needed 2 3-input AND gates, and because it was positive logic, we were using a OR gate, a 2-input OR gate. and then just wire up the Boolean expression using A not A, B not B, C not C, and D and not D. Make sure you wire to the right place. Then we place a wire label, and I can call that segment A. I'm going to call it SA. I could have put a wire up to the 7-segment display, but this shows you how to use wire labels. I'll make another wire, and I'll also call that SA for segment A. So they are now connected as if there was a wire between them. I'll just add wires and wire labels for all the other segments. You can right click to place a wire label, or you can go into wire label mode. And you can see I've connected segments B and C together and segments E and F together because they had identical Boolean expressions. So for segment B, I'll put the gates that I need. That was not B and A. Place a wire label, call it SB for segment B, which is also connected to segment C because I physically wired them up here. And I'll right click this, place a wire label and call it SB for segment B. And because it was negative logic, for segment D, we'll use a NOR gate. Place a wire, and I'm going to call that with a wire label SD for segment D. Not C, not B, or C and B. That was the Boolean expression for segment D. Go to the 7-segment display. Don't forget to label the segment with the same wire label, SD, so they're connected logically. I'll call this SE for segment E, which is also wired to segment F, and then I'll call this SG for segment G. Drag this down to where I should have put it in the first place. Now for segment E, which is the same as segment F, we've got a 3 and a 2 input AND for the Boolean expression, and it was negative logic, so we'll use a NOR gate to make it positive again. Place a wire label, call it SE. We have not C, not B, and not A. It would be OR, but it was negative logic, so we use a NOR gate. It's going to be C and B. So that is for segments E and F. So let's do segment G, last but not least. Positive logic, so we use an OR gate. Place a Y label, call it SG, so it connects to the G segment. Not C and not B and A, or not C, B and not A. Make my clock a bit slower and simulate. So it says HELLO, then it'll be off for 2 cycles, off for the first state, and then HELLO, etc. Speed it up a bit. So it's doing what we wanted it to, so that's great. But what we're going to do next is introduce a shift register delay line to have multiple 7-segment displays. We've got segments A, B, C, D, E and F, although some of them went through a NOR gate because it was not this and not that. And when you put them through an OR gate, it gives you the positive output. So these are going to our 7-segment display, and it's saying hello. So it's saying H, then E, then L and O. And there's, because hello is HELLO, 5 characters, and we've got a 3-bit count from the clock inputs was C, B and A. We had 3 opportunities to put other characters, but I chose to put blanks. You could have said hello and then 3 more characters. But anyway, that's not important. But what is important, I think, is to get some more 7-segment displays, because it's all very well it's scrolling through 1, but what if we had 5? If we took the first one and made it the rightmost 7-segment display, so I'll do that, I'll drag this and put it over here. So this is our first 7-segment display. If we had a second one and a third one, 4th one and a 5th one, it'd be great if we could start off with it saying H, then HE and HEL and so on, then all the way over to the 5th one, which would show the full message. And we can do that using basically a shift register. So a shift register is basically D-type flip-flops, where a data signal put in here will be delayed by 1 clock cycle, and then it'll appear here, then delayed another clock cycle, and it'll appear here, and so on and so on. Because if you know how flip-flops work, you've got your data input, your Q output, not Q output, and your clock signal. If we put data in, say this was the data coming out of or going into segment A, then what comes out here is the same data delayed. And then if we put it through another flip-flop and we clock them at the same time, this will be what's coming out here is A delayed twice. And what we can do with A that's been delayed once, so this will be normal segment A. What we put in here is A delayed once. I could call it A1. So I'll wire that up to A1. What comes out here I could call A2. And so on, A3 and A that's been delayed 4 times. And I'll do the same for each segment, you know, for B, then I'll have B delayed once, B delayed twice, B delayed 3 times, and B delayed 4 times, all the way down to G. So what we need is a shift register. Now, it's pretty arbitrary or random in my choice of having 5 7-segment decoders. We could have had more or we could have had less, but because it's a 5-character message that I've chosen to do hello, it'd be nice to have 5 7-segment displays. So let's get on with making that happen in Proteus. So remember, I labelled segment A as SA, segment B I labelled as SB, and of course the segment B and segment C are connected to each other, so I didn't need to create more logic for segment C. I just tied these 2 segments on the display together. Then segment D is on its own, but segment E and segment F are identical, so I've wired them together, and segment G has its own expression, so I labelled this wire as segment G. So I need some more 7-segment displays. I need 4 more. I'll zoom in a little just so I can place them neatly but still give myself a bit of space. So there's our 5 7-segment displays. Just make sure they're all grounded. The next thing I need to do is to wire up the 7 segments in the same manner as I did the first one. So I'll go into wire label mode. It's easier than right clicking every wire. So this is going to, I can call it A1, or to be consistent, segment A delayed by 1 clock cycle. Segment B1, segment D delayed by 1 clock cycle, and so on. Now we need to get this 4094 shift register, and we need 5 of them. We need 1, 2, 3, 4, 5 to delay all 7 segments, because we have 2 groups of common segments. If we had 7 different Boolean expressions for the 7 segments, then we'd need 7 of these shift registers. So what I'm going to do, I'm going to put segment A into the data input of the first one. So this is exclusively for all of the A segments. I could come up, and this is going to be for the B segments. This is going to be for segment D and all the subsequent delayed segment Ds. So I could just place a wire label on the input. The data is the input. Put SD instead of dragging a wire over. Segment E, so this will delay the E segment. F is already accounted for because it's wired up to all of the E's. And segment G is going to go in there. So we can use wire labels instead of wires as long as the other end is called the same thing. Segment A will have a value on it. Say it goes to 1 when the first segment A lights up. That will go into this data input on pin 2, and after a clock cycle it will appear at Q0, which is the output of the first flip-flop inside. 1 clock cycle later it will appear here, then it will appear here, then it will appear here, and so on. We've got more flip-flops than we need. So we've got segment A coming in, then this will be segment A delayed by 1 cycle, which I've called SA1 down here. This will be segment A delayed by 2 cycles, segment A delayed by 3 cycles, and finally segment A delayed by 4 cycles. I'm going to call this clock so that I don't have to wire the clock up to it. I need a 5-volt supply for pins 1 and the output enable. If you look at the data sheet for the 4094, you'll see why. A DC supply. Be high, but I need to call it something, or leave it what it's already called, but I need to make sure it has 5 volts as a logic 1. Let's simulate this and see what happens. Whenever segment A goes high, it chases after a clock cycle to the next 7-segment display. So let's continue that in the same way for all of the other shift registers. Could move this over a little bit. You have to be a bit careful that the wires don't touch or become connected to each other when they're not meant to. So this is segment A delayed by 1, 2, 3 and 4 clock cycles. So this will be segment B delayed by the same. So in wire label mode, this will be SB1 and so on. And segment B delayed by 4 cycles. Now segment C was already taken account of because it's wired up to segment B for each of these 7 segments. So this is going to be segment D delayed by 1 cycle. Segment D delayed by 2 and so on. All of the STB and output enables are connected to the common 5 volts, and all of the clock signals are connected to the main clock. So we'll click on simulate and see how it works. That is pretty cool, to be honest. And you can change the message by changing the logic that we came up with here, but you wouldn't have to change everything with the shift registers. What you would need to, if you had 7 different Boolean expressions, one for each segment, then you'd need 2 more of these shift registers. But as it stands, we had a little bit of time saved because some of the outputs were identical. So that is pretty nifty. You should have a go yourselves. So please comment below with anything that you'd like to understand more, or tell me any other videos that you'd like. So it's hello and goodbye for now.